I'll be talking about ergodicity breaking in flatbands and more generically about flatbands, how to construct them and how to perturb. We're done in collaboration with these people, mostly from our center. So Sergei Flach, who's here in the audience, then Chadish, our postdoc, Youngjun Lee and Youngjun Kim, sorry, and Sang-Hoon Lee, who are PhD students. Mitun Tudiangal, who was a postdoc at our center but has since moved, and Carlo Danieli, who's also a postdoc and now moved to Rome. Ihor Bakulchik, also an ex-PhD student of our center, who has now moved to industry. Arindam Malik, again a postdoc at our center, who's now in University of, who's now in Poland. Ulaimu Maimaiti, whom some of you might know under the name of Ibrahim Muhammad, who was our PhD student and then moved to Rutgers and now to industry, and Nana Chang, who was a visiting PhD student. She's now back to China, to the Tsinghua University. So the brief outline is, well, I'm first going to talk about what are the flatbands and briefly motivate why they're interesting to look at. There were already a few appearances of flatbands during the conference, the talk of Martin, and I believe in a few other occasions. We'll then discuss how we can construct them in a systematic way and basically on demand in various settings, varying the dimensions, the geometries, and briefly touch on Floquet and many body settings. And finally, once we hopefully present how we construct flatbands, I will describe what happens when we break them by doing various perturbations. And I will mostly focus on disorder, nonlinearity, and interactions. Okay. So the big picture of why flatbands are interesting is essentially the idea that we have a macroscopic degeneracy due to the absence of dispersion. And then we add some perturbation and we ask what will happen. And the expectation, based both on our intuition, some experimental results, and the known works, is that quite often various interesting phases emerge due to the fact that any perturbation is relevant due to the degeneracy. And flatbands, I'm going to talk about just one example at the single particle level, but one can also design macroscopic degeneracy in many body settings. And a few examples, I'm typically showing a Landau levels and quantum Hall effect, flatband ferromagnetism, flatband inherits superconductivity, and also I think the classical spin liquids with, say, the emergent monopoles is also one example of what happens when you have macroscopic degeneracy. So the more technical definition, so a lattice flatband I'm going to talk about is dispersionless band in a tight binding network with short range hopping. In that case, they typically host compact localized states. You can show that the eigenstates of such band, you can find eigenstates of such a band which occupy a strictly finite piece of the lattice. They will prove to be very useful. One immediate remark is that obviously such bands are fine-tuned. You don't get it for just an arbitrary set of hoppings. You have to impose some constraints, and therefore they're fragile to perturbations. And as I was mentioning already, being in proximity to a flat band tend to stabilize exotic phases and unconventional orders or enhance the stability of the others. Here are a few examples, simple examples, like the diamond chain that I think already has shown up during the lecture this morning, or the 1D the 1D Lieb or the stub lattice. As you can see, or the sawtooth chain or the 2D dice or the 2D Lieb with the corresponding compact localized states. So these geometries look pretty different, but they all share in common a flat band marked in red in their spectrum. So the question is then, how do you construct them? The examples I've shown so far are the ones that were discovered by various people over time. And also a number of different methods were more or less systematic were proposed how flatbands can be constructed. One way to go is to rely on specific symmetries like chiral symmetry. So if you have a chiral symmetry, your spectrum is guaranteed to be symmetric with respect to zero energy. Now, if you have a mismatch in the number of sites on different, say, two sublattices, you're guaranteed to have a flat band. You also have local symmetries or latent symmetries or anti-PT symmetries, as I will touch upon, that also guarantee the existence of flat bands. You can rely on graph properties. The most famous one is line graph, and that's how you get flat bands in paracolor lattice or, say, Kagome lattice. And a number of other methods, they all share the common problem of being non-generic. They all rely on some property that you expect. Therefore, the outcome is also a set of flat bands that is probably a submanifold of all the flat bands. So they're not systematic. And natural question is that we want to make a systematic study so as to see, also be able to see systematically what kind of effects we get if we have perturbations. And so to address that, what we ended up with understanding is that a systematic construction is indeed possible and is quite straightforward. And it amounted basically to understanding what are the relevant parameters for the systematic construction. It turned out to be the dimension of the lattice you're interested in, the number of bands you want to consider, the hopping range, which is always finite, but you can consider nearest neighbor or second nearest neighbor, or you can go further. The CLS size, if you remember the compact localized state, turns out to be the crucial building block in this construction. So, some sense, the way of the construction is actually by fixing the CLS size or its shape, optionally adding lattice symmetries, which gives you the CLS amplitudes. And based on that, you're basically solving an inverse eigenvalue problem. You know what your eigenstate is, and you want to reconstruct the Hamiltonian. And eventually might also want to consider band touchings. This could be incorporated into the scheme. And so what happens then is, as I was saying, you fix the dimension, number of bands, hopping range, the CLS size, and also actually fix the flatband energy. This in turn imposes some constraints on the amplitudes of the CLS, not arbitrary fine compact localized state can be an eigenstate of a Hamiltonian. Then by solving the inverse eigenvalue problem where you know an eigenstate, you want to reconstruct the Hamiltonian, you get, you reconstruct the flatband Hamiltonians. In the simplest case, you can consider the two-band setting just a ladder. And what you need to do is to set the CLS and then just make sure that under the action of the Hamiltonian, this is an eigenstate. So if you act on this probe state with your Hamiltonian, it doesn't spread out. In principle, lattice geometry can be incorporated into this construction by assuming that some hoppings are absent in the generic scheme. You can extend it to the non-Hermitian setting, and eventually this also helps to solve another problem. If you have a flat band, how do you find the smallest possible compact localized state? That would be important in what follows. And you can invert this scheme and just by considering compact localized states of larger and larger size, identify the smallest possible one. So we carried it out for a number of systems. In particular, we played with this two-ladder setting and considered what kind of flatband Hamiltonians we can discover in this setting, which corresponds to resolving this set of equations where H1 and H0 correspond to the hopping inside the unit cell and between the neighboring unit cells. So this case can be solved analytically. And one important result we discovered is that despite being fine-tuned, flatbands actually organize themselves into manifolds. And in particular, in this case, you have a whole set of two disjoint manifolds parameterized by two angle parameters that where you can change these angles and maintain the flatness of the band. What this taught us is that despite being fine-tuned, flatband Hamiltonians are not isolated in the Hamiltonian space, and typically you have perturbations, single particle perturbations to the Hamiltonian that will keep the flatness of the band. It just so happens that most physical perturbations we would want to add to the Hamiltonian, they don't belong to this class of perturbations that conserve the flatness of the band. The one drawback, though, of this construction is that you indeed can find systematically all the possible Hamiltonians, but the hoppings are in general might not be nice in the sense you typically get all the possible hoppings between different sublattices. And the known examples typically correspond to some specific points in the space of the Hamiltonian, of the flatband Hamiltonians. This can be easily extended to the two-dimensional setting, albeit at the expense of slight increase in technicality, because now your compact localized states are not characterized just by this size, but you also have to consider various shapes. And the condition that it's a compact localized state that is under the action of the Hamiltonian, it doesn't spread out, becomes more complicated. But that still can be worked out, leading to a generic flatband generator. I mean, this might look complicated, but actually it still solves the problem if you give me a lattice with perhaps some constraints and ask me to produce a flatband Hamiltonian, these schemes work really well. There's an alternative construction which was proposed by the group of Bomdung Yang at Seoul National University and Raff and Pichon in Orsay, if I remember correctly. It's based on the alternative block space construction, where instead of looking at real space and all the constraints, you can start again with the CLS, but in the block representation, and then basically reconstruct the Hamiltonian, requiring it to be basically a linear combination of projectors onto the given block wave vector. To give a simple example how it works for the simple Lieb lattice. So here is the Bloch Hamiltonian of the tight binding Lieb lattice with just nearest neighbor hopping, where QIs are exponentials of IK AI and AI's basis vectors. And then you can easily check that this is an eigenstate of this matrix. And if you now construct two orthogonal vectors to this block wave vector, you can follow this recipe to construct flatband Hamiltonians with band touch. Any questions so far? And I'll move on. So here I'm stepping outside the systematic construction, going into more specific direction. So I was talking so far about flatbands that feature compact localized states, which would be important in what I'm going to tell. But flatbands can also be found in a different context, namely, for example, in the absence of translation invariance. So if you consider the effect of the electric field, in 1D, you find the Wannier-Stark ladder, where the spectrum is just consisting of isolated equidistant levels. However, in 2D for Brevet lattices, whenever the direction of the DC field is commensurate with the lattice, you can demonstrate. It's possible to demonstrate that the spectrum is consisting solely of equidistant flatbands, which in some sense resembles the Floquet-driven systems, and that's no coincidence. You can actually also show that in this case, there's a mapping, there's an exact mapping to a driven model, which has just single flat Floquet band. This mapping holds at the single particle level, but I should just warn you that if you add perturbations, it doesn't generically hold. This can be further extended. I'll just touch upon it and not go into the details. You can also, that's where the antipede symmetry comes into play. You can demonstrate that the antipede symmetry generically protects zero energy flatband, since antipede symmetry also enforces the symmetry of the spectrum with respect to the zero energy, but it also protects this flatband in the presence of the DC field, which is not a given, since, for example, if you take a Lieb lattice, which has chiral symmetry, which ensures a flat band at zero energy, and you add the DC field, the flatness of the band is gone. Okay. So far I was talking about a single flat band. Now I'm going to consider an even more fine-tuned case, but which will be relevant for the scenarios where I'll consider the perturbations, namely what happens if you require all the bands in your system to be flat. This is obviously even more sensitive to perturbations, and quite obviously this corresponds to the case of a full localization. The particles cannot move since all the group velocities are zero. This looks quite complicated, but actually in 1D, we have demonstrated that there's a very simple and exhaustive construction of all such bands. Namely, you can just start with a set of decoupled sites, assign to them different on-site energies depending on the sublattice, and then just apply local unitary transformations which generate the hopping network. So one example, the two-ladder system is provided here. So you just start with two empty sublattices, you apply one unitary which couples sites in the same sublattice, then you redefine the unit cell by, say, shifting the two legs of the ladder, and then you apply another unitary transformation that couples these two, coupled sites in the new unit cell, and this way you end up with a fully connected, with a network that is fully connected, but yet by construction has only flat bands because unitary transformations do not change the spectrum. And for example, in 1D, the well-known Kreutz ladder falls into this class. So now in 1D, this construction is exhaustive so long as your hopping range is finite. In higher dimension, we believe this is also true, but we do not have a proof yet. So let me make an intermediate summary. So I hopefully demonstrated a systematic construction of flat bands in real and Bloch spaces. It relies on the compact localized states, which is a fundamental block, and applies to any space dimension lattice topology. And we find that flatband Hamiltonians are not, despite being fine-tuned, they're not isolated points in the Hamiltonian space, but are part of manifolds. So you have perturbations that preserve the flatness, although the hoppings might be ugly. So there are several extensions one might think of, for instance, non-Euclidean geometries like hyperbolic spaces where experimental realizations of, say, hyperbolic versions of the Kagoma lattice were made recently, or the absence of translation invariance like the DC field that I have discussed, or the quasi-crystals, or even completely disordered patterns. Especially, well, one question that intersects with the topic of this workshop is the driven systems. I've demonstrated one simple example of the DC field inspired 1D chain with a flat band, but there surely are others. And for instance, there's one poster discussing driven dynamics where you also have dynamical localization and extensive degeneracy and, well, other cases. So now, having understood how to construct flatband Hamiltonians, I will now move on to discuss what happens if you now add various perturbations. I'm mostly going to focus on disorder and interactions. I'm going to discuss the case of macroscopic degeneracy, flatband plus a perturbation, and I will focus on the case of the all-band flat systems for reasons that will become clear in a moment. So the main message that I have is that different flatbands react differently. So if you add perturbations, then different parts of this flatband manifold of the flatband Hamiltonians will show different reaction. And another important observation is that actually further fine-tuning is possible. You can actually combine flatband networks and the perturbations in specific ways to achieve further, so to say, degeneracy or desired properties, which I will illustrate. And finally, more technical remark is that the basis of the compact localized state turns out to be instrumental in understanding the effect of the perturbations. So let me start with the disorder, since that's just a simpler single particle perturbation. So we look at the case of the extensive degeneracy plus disorder, and we want to understand what that gives. Typically, disorder leads to localization. So what will happen? So the answer, it turns out, depends on the type of the flatband the presence of the gap and the disorder itself. So the few things that were known before we started our investigation was that in the case of the weak disorder, if you take a flatband, you had a weak disorder, you wonder how localization length scales in the limit of the weak disorder. It turns out that it exactly depends on whether flatband is gapped or touching dispersive band or even crosses the dispersive band. Depending on that, the scaling weak disorder of the localization length is different. You can observe interesting reentrant localization where by taking a flatband heading disorder, you basically delocalize your system, which then localizes again once disorder becomes stronger. And this was even observed experimentally again for the simple diamond chain. Finally, an example of critical states where again you take, in this case, a checkerboard lattice with a band touching, you had a bit of disorder. And what was claimed by Pragya Shukla and John Chalker is that you get critical states. So this already shows that there are a lot of different phenomena occurring in the presence of disorder. What we were curious to understand is, well, is that all, or can we understand it in a more systematic way? That we took the all-bands flat Hamiltonians, or rather the generator that allows us to sample the entire manifold. We consider the case of adding weak disorder and understand what is happening. So now that's where the fact that these all-band flat lattices can be constructed by local unitary transformations comes helpful. An equivalent statement is the construction by local unitary transformations is that the CLS are orthogonal. So if you take a CLS, you shift it, the overlap is always 0. What that allows us to do is basically take the all-band flat Hamiltonian, add the on-site disorder, or actually any other single particle perturbation, and just revert the construction that we did. So originally we started with decoupled sites, and then we started applying local unitary transformations, coupling, say, sites in the same unit cell and sites from the neighboring unit cell, and getting the Hamiltonian. Now we have disorder, and we just revert the construction, which leads to an effective Hamiltonian, which turns out to be easier to analyze and also highlights the properties. And in this particular case, where there's just, say, you just add a disorder, what turns out is that the strength of the disorder becomes just a multiplicative factor in the final effective Hamiltonian. And you see that macroscopic degeneracy plus weak disorder is equivalent to some effective model at finite disorder. So to sum up the results, which were mostly numerical in this case, is that in 1D we find basically localization, no matter which all-band flat model we take. The only interesting observation is that we get Dyson-like singularity in the zero energy state. In 2D, again, all the states are localized for the standard on-site disorder. There's also a zero energy state. By considering other classes, other symmetry classes, it's possible to induce delocalization, but which is now non-perturbative. So this delocalization is not driven by the strength of the disorder, but rather which part of the manifold of the all-band flat lattices you're sitting on. And 3D is just corresponding to complete, well, in 3D, as we were expecting, we do observe the same delocalization even in the standard class with just on-site disorder. Again, depending on where on the all-band flat manifold you're sitting. Another type of disorder perturbation that we looked at, which is pretty standard, is the weak quasi-periodic potential. In which case, again, you take the all-band flat Hamiltonian, you had weak quasi-periodic perturbation. And the question is, in the standard Aubry-André model, one finds a metal insulator transition even in 1D. So we looked at the 1D case. What turned out is a more complicated effective model. So again, as I explained in the previous slide, a flatband plus this quasi-periodic perturbation leads to an effective model, which in this case corresponds to a model with both quasi-periodic hopping and on-site potential. And it turns out that for some specific cases, it maps exactly onto the extended Harper model and off-diagonal Harper model, both of which feature phase diagram with both localized, extended, and critical states. In our case, though, what we found is that we either find localized states, it's basically whenever we don't see this mapping, or critical states corresponding to the critical region of the extended Harper model, the off-diagonal Harper model. As we increase the strength of the disorder, so as we go from infinitesimal disorder to finite one, the critical spectrum turns into discover mobility edges from localized states to critical ones, which in some cases even persist up to arbitrary disorder, arbitrary strength of the potential. Okay. So this is basically what is the effect of the single particle perturbations. We see that we can induce a non-perturbative delocalization and eventually reentrant behavior, since it's clear that, say, in the disordered case, if you make the disorder infinitely strong, the system should localize back. Things get even more interesting in the case of interactions. Again, let me briefly summarize what was known before. So if you consider all band flat lattices and you had, say, Hubbard interactions, at the single particle level, there was no transport. If you add interactions, well, what was known is that in some cases you observe transport of pairs. Single particle cannot move due to the fine-tuning at the single particle level. However, interaction induces the transport, but it can only be done in pairs of particles. And this will have important consequences, I will say. It is also possible to engineer quantum scars in this case, that is, eigenstates that have low entanglement. And typically what happens is that you can combine the all-band flat lattice or even a flatband lattice and the interaction in such a way that the compact localized state is annihilated by the interaction and thus survives in presence of the interactions. Another interesting known result was the realization of the SYK. It was proposed that if you consider by Tigran Sedrakan at the University of Massachusetts, if you consider a Kagome lattice with a bit of disorder, bit of impurities and interaction, again, in the weak interaction limit, it maps to an effective SYK model with the all-to-all description. Any questions? So now if you want to understand, again, systematically the effect of the interactions, what we do is we repeat the steps we did for the single particle, the disorder case. We take the all-band flat manifold, we add the interaction, and then we reverse the construction, this sequence of unitary transformations, local unitary transformations that led to the all-band flat network. We add the interaction, we reverse it, and we end up with a new effective model, which again, we expect would highlight us, would provide some intuition on as to what is the effect of the interaction. So again, the main observation is that further fine-tuning, as I was mentioning, of this this generic interaction is possible. So if you go into this effective model, what you find is just the original on-site energies. So this is the diagonal single particle part, plus in general, generically, you will find some horribly looking two-body interaction terms, which comprise both the density-density term, and just generically density-assisted hopping or pair moving. So to get some intuition, we looked at the nonlinear version of the model first. So instead of looking at the Hubbard interaction, we just considered, say, Kerr nonlinearity. And it turned out that fine-tuning of this generic interaction is possible. That is, combining the all-band flat lattice geometries and the type of nonlinearity allows you to kill some of these terms, and for instance, end up with just the density-density terms plus these terms, which in the quantum case exactly correspond to taking two particles on one side and moving them coherently to another side. And what this translates into the nonlinear case is caging of interactions. So if you now transform this into the Schrodinger equation, quite easy to convince yourself that whatever initial excitation you have, it has no chances of propagating, precisely because of these terms. Since, well, if your equations of motion will be basically governed by the derivative of this effective Hamiltonian with respect to A or A complex conjugate. And at any given site, there will also always be a linear power of the amplitude A, which guarantees that excitations cannot propagate. And this is indeed what we observe numerically. So for special cases where the nonlinear Hamiltonian reduces to this form, the initial excitations persist, while if you deviate by looking at a different, say, initial odd-band flat model, you will see some spreading, which is actually happening subdiffusively. If you now go back to the quantum problem, the very same fine-tuned sum manifold with only these terms present corresponds exactly to the case that I mentioned earlier, the transport of pairs. As you can see here, the only way for particles to propagate along the lattice is by in pairs. You annihilate, you take two particles on one side, move them to a different side. And this also immediately tells you that there should be trapped particles, since if you happen to have on some side, and say if you consider bosons, you have an odd number of particles, one of them has no chance of living because you're always changing the occupation number of any given side by 2. This leads to, again, to quantum scars, which in this case might depend on the interaction strength due to the density-density terms. However, quite unexpectedly, further fine-tuning is possible. So here, I killed the generic density-assisted hopping terms, but I can still move the pairs. One might wonder whether one can kill the pairs and just end up in a situation where nothing moves. Surprisingly, this is possible, and this was already pointed out as a possibility in the original work by Tovmasyan and Päivi Torma in 2018. However, they didn't provide a specific example. And then the group of Yasuhiro Hatsugai, they proposed a specific model where this was observed. They actually considered spinless fermions on a Kreutz ladder with nearest neighbor interaction, and demonstrated that in this case, there's no charge transfer and it's suppressed. And the mechanism behind is exactly suppression of these terms. So if you diagonalize with the local unitary transformations, if you diagonalize this system in many body Hamiltonian, you will discover that you don't have any single particle terms that allow particles to move, and also at the many body interaction level, you only get density-density. This actually can be generalized. That's what we dubbed as many body flatband localization. You can construct, basically, there's a prescription how to combine the all-band flat single particle Hamiltonian and the interaction so as to end with non-interacting so as to suppress the charge transfer. And the idea is pretty simple. You just want to make sure that you say in the simple two-ladder case, you start by again decoupled sites. You apply unitary transformations to pairs of sites so as to end up with dimers where particles can hop within the dimer, and then you add the interaction that connects only the ends of the dimers, so that they're making the next step to entangle these two sides. It preserves the density-density form of the interaction, but provides you with the full hopping. So this is the very simplest case and exactly the one of the original Kreutz model with interaction, but it can be extended to other lattice geometries and also other interactions. And since, yeah. Okay, yeah, then I'll speed up and part. Yeah. Okay, so let me explain one last thing. So I demonstrated how the particle transport can be suppressed in this setting. However, you might still wonder whether heat transport is possible. You can imagine that even though you're, if you go into this basis, even though your particles cannot move, you can imagine that you, by driving the particle within a single dimer, by having the density-density interaction, you can induce some heat propagation over the lattice. So the quick answer is no. in 1D at least, because everything in this case starts depending on the initial condition, namely how you populate these dimers. So if you think of a 1D chain and about various initial conditions, it's easy to see that if there's just one dimer that is empty, it cuts the system in two and no heat transport is possible. This is happening with probability 1 for a long enough chain. This tells us that in 1D, heat transport is is exponentially suppressed with the system size, and then thermodynamic limit is absent. And what happens in higher dimensions is more complicated because now, again, the idea is the same. You have to consider the initial distribution of particles on the lattice of interest. And again, the empty dimers would play a crucial role. You have to consider, it basically boils down to a percolation model, ensuring that at low enough filling fractions, there's no heat transport. Okay, I'll stop here by giving the conclusions. So we found a way to systematically construct short-range translation invariant flatband Hamiltonians in both real space and Bloch space, and also systematic construction of a Hamiltonians for the case with all bands flat. And we've studied various perturbations, disorder, and interaction, showing that you can, well, having a systematic control over the flatbands, you can also construct various classes of models with controlled properties. And well, there are some future directions which I just leave here. And with this, thank you for your attention.
Okay. So yeah, are there questions?
So thank you very much for this interesting talk. So yeah, I have indeed, as you mentioned, there is a similar. The model we studied was strongly interacting spin model, which, I mean, it has no well-defined notion of bands, but I'm still thinking, is there some connection, right? So what we do have is that like these localized dynamical symmetry type things that kind of pop out because you have some geometric constraints. So I'm wondering, can your method be used also to, so it's kind of like a flat bands that are not degenerate, but they're equally spaced in energies, let's say. This is what you can, this is kind of what you can see. You have a localized thing, so you can expect to have something that's, if you insist on defining it the K-space, it should be kind of flat, but because you have these oscillations and so on, you have some sort of degeneracy in the energies, energy spacings, not the energies, let's say, yeah. So can your method be applied to construct such models as well? That's my first question. And my second question is maybe scars also. I guess we can discuss if it's like really scarring, because scars, if your models have this, then I'm pretty sure that it's not like scarring in the sense that you get only oscillations from specific initial states, yeah? Mm-hmm. It's generically, you get oscillations generically, yeah? So that's two things, yeah.
Yeah, well, as to your first question, I mean, we really need the degeneracy. Well, rather we need the compact localized states, preferably orthogonal one. Then we can do this then we can basically do single particle diagonalization that remains local, which is, say, if you have dispersive bands, which is not the case.
Yeah, but let's say instead of degeneracy, you have degeneracy in energy, you have degeneracy in just the energy spacings.
Well, then I guess it's probably would be related to something like harmonic oscillator. That's what I would think. But again, in your case, I guess many of the properties, I mean,
it's very similar, yeah.
I mean, it's dictated by the diamond chain, which happens to be, it's a bit of an, like in a good sense, it's a bit of an oddball in the flatband. Among the flatband Hamiltonians, because you can show that it has to have flatbands by several different mechanisms.
Yeah,
Unrelated, and therefore I would just expect that things might work due to well, it's just enough that something works due to one of these mechanisms. But otherwise, I think it's better to see the Hamiltonian, and then probably be clear if our methods apply. In general, I mean, generically, my understanding is that these flatbands can often, but I'm not sure that always, be translated into the spin systems. There's definitely a relation between, let's say, all the frustrated magnets with huge degeneracy in the flatbands, but I'm not sure it's a one-to-one correspondence.
yeah. Even the thing we have is not necessarily frustrated, so it's okay. Thank you.
Here's time maybe for one last question. So actually, I have one. So if I understand correctly, most of your talk was about building a flatband out of localized states.
Yeah.
Does the opposite prescription work? If I give you a flatband, you can find for me the localized state. Is it always the case? I remember in the case of Wannier function, there is an ambiguity of how you build it.
No, here it's pretty much, it's simple. So so long as you, I keep forgetting the exact argument, but so long as you have finite range hopping, you have a flatband, you're guaranteed to have no, okay, let me be precise. So long as you have finite range hopping and translation invariance, you're guaranteed to have a compact localized state. I mean, if you don't have translation invariance, then DC field is one example I didn't mention, but for this, say, square lattice with a commensurately directed DC field, you get flatbands, but they don't have CLS. Right, and as to, I mean, obviously CLS are not defined uniquely, because if you have one, you can take its translated copy, make a sum, and it still works. But what you can always work out is the smallest possible one. Okay, thanks. So this is thanks, Alexei.